fire off an action potential and then immediately fire another one, the muscle cell does not have time to relax. That's what you're seeing in the B area. Before that muscle cell could finish relaxing, another action potential has stimulated it to contract again. And that second contraction, because it has not quite relaxed, is a bigger one. So every time the neuron fires off an action potential, the muscle cell will contract. And if it's not given time to relax, it will contract harder. And if you get enough of these action potentials, it could hold the contraction. So if you were to put your hand into a ball and kind of close your fist up and squeeze and hold it, you're holding that contraction because your neurons are constantly firing off at the muscle cell to keep it contracted. And when you relax, it's because you stopped firing the action potential and you've gotten rid of acetylcholine and you've put your calcium back into the sarcoplasmic reticulum. And again, not only can you hold a contraction, remember, we could change the force. This is just like us again talking about the motor unit. Remember, a motor unit is just a motor neuron and all the muscle cells it will stimulate. And remember, if you want a very weak contraction, you just want to move a little bit or generate a weak, brief force, you're just going to use very few motor units. But if I want to have a long, sustained contraction or generate a great force, I'm going to increase the number of motor units. And we even give a name to that. When you increase the number of motor units, either to sustain a contraction or increase the force of a contraction, we call that motor unit recruitment. Motor unit recruitment is just when you increase the number of motor units to either sustain a contraction or increase the force of a contraction. And like always, luckily, we're not thinking about this. This is things our muscle cells are doing on our behalf. What else? Turns out you know a lot about skeletal muscle cells and skeletal muscle tissues now. So now we could talk about some exceptions to some rules. Turns out I kind of lied to you at the beginning of this chapter. How? Well, I told you we're talking about skeletal muscle. And I told you at the beginning of this chapter, you do control skeletal muscle. It's voluntary. Well, it turns out not all the time. Sometimes you have involuntary contractions of skeletal muscle, meaning sometimes skeletal muscle will move without your permission, and it happens quite often, and we give a name to it. It's called muscle tone. Muscle tone is just when you have involuntary contractions of skeletal muscle, but for good reasons. Why? When do you have muscle tone? Well, it turns out you have a lot of muscle tone in your back muscles. The muscles in your back are skeletal muscles, so you could use them if you wanted to, but it's also contracting without you thinking about it. How do you know? Well, it turns out if the muscles in your back were to relax, you would fall and slump over due to gravity. But because your muscles are contracting, you're either sitting up straight or you're standing up pretty straight. Why? Because they're contracting without you thinking about it. You're having muscle tone in the skeletal muscles in your back. So yeah, if I ask, skeletal muscle is still voluntary, but there is something called muscle tone. There are occasions when it can contract involuntarily. What else? Oh, we know how a muscle contracts, but you might not know that there are also different types of contractions. Turns out if you wanted to work your muscles out, you have multiple ways to do it because there are multiple types of contractions. And I want you to know these two major types of contractions. There's an isotonic contraction and an isometric contraction. Let's go one by one. Like usual, don't be intimidated. The names give you a hint. Let's start off with isotonic. Iso, just break the name down. Iso means the same. Tonic is for tone, as in tension, as in the force your muscle can generate. So in an isotonic contraction, the force or the tension will stay the same, but the muscle length will change. That's an isotonic contraction. It's when the force or the generation stays the same, but the muscle length changes. This is actually what you think of when you think about lifting weights. Lifting regular weights, think of doing bicep curls. Imagine having a 20-pound dumbbell. And when you're doing your bicep curls, that 20-pound dumbbell in your hand doesn't change. Doesn't matter if you bring the dumbbell up closer to the shoulder or you bring it down closer to the hip and knee. When you're doing your bicep curls, you constantly have to hold this 20-pound dumbbell. So you will constantly generate this force to help you to hold this 20-pound dumbbell. But as you're doing your bicep curl, when you bring the dumbbell up, where you're contracting the muscle, you're shortening the muscle. And when you bring the dumbbell down, you're lengthening the muscle. So the muscle length is changing, but you're still generating the same force to hold your dumbbell. You're doing isotonic contractions when you lift weights. And this is anatomy. We name everything. We even give names to the different time periods when the muscle length changes. We give a name to when the muscle length is long and when it's short. When you shorten the muscle length during your isotonic contraction, we call that the concentric portion. The concentric portion is when you shorten the muscle. And then the eccentric portion of your isotonic contraction is when you lengthen the muscle, when it gets longer. So that's your isotonic contractions. And then there's one more way. If you don't like lifting weights, don't worry. There's another way to work out because there's another type of contraction. It's called an isometric contraction. Again, don't be intimidated. Just break down the name. Iso still means the same. Metric as in a unit of measurement, possibly for length. So think length for metric. So in an isometric contraction, now the muscle length will stay the same, but the force or the tension will change. So isotonic and isometric are basically opposites. In an isometric, the muscle length will stay the same, and the force or the tension will change. What's an example of an isometric contraction? Well, an example is what you see on the next slide of this young man holding a book. All the way to the right in segment C, that's an isometric. He's holding that book in his extended hand. And I could force him to generate a bigger force if I just added another book on top without him moving his arm. That's a type of isometric contraction. Or another example of an isometric contraction is pushing against a wall. You could push against a wall hard with as much force as you want, or you could push against the wall gently. But you don't necessarily have to move your arm as you're pushing against the wall. So your muscle length is not going to change, but the force you use can change. That's an isometric contraction. Again, keep it simple. Isotonic contractions, the tension or the force stays the same while the muscle length changes. And when the muscle gets shorter, call that concentric, and longer is eccentric. And then isometric contraction is the opposite. It's when the muscle length stays the same and the force or the tension will change. That's it. That's your different types of contractions. And again, there's a couple other things to talk about. Not only do we know the different types of contractions, we could actually go back microscopically again and look at the skeletal muscle cells. You know what a skeletal muscle cell looks like already. So now we could complicate it. Turns out, not only do the different types of muscle tissues differ, but cells could differ. When we look at the different skeletal muscle cells, they are not all the same. Turns out there are three major types of skeletal muscle cells. Remember, a muscle fiber is just another name for a muscle cell. And there are three major types. There are slow oxidative muscle fibers or muscle cells. There are fast oxidative glycolytic muscle cells. And there's a fast glycolytic. And like usual, they give you a hint in the name. These are all muscle cells. They're all moving. They're all contracting. Turns out this slide lists them in order of speed. And they tell you the name. Slow oxidative fibers are the slowest of all three. They contract the slowest. Fast oxidative glycolytic fibers are kind of in the middle in terms of the speed of their contractions. And fast glycolytic fibers are the fastest of all. Why do their speeds vary? It has to deal with how they use ATP. And to use ATP, your muscle cells actually use an enzyme. No, you don't need to know it. But how much energy you use will actually affect how fast you could contract. So if you use a lot of energy quickly, you will contract quickly. While as if you use or burn through your energy kind of slowly, you will move a lot slower. So your slow oxidative fibers are the slowest because they use energy kind of slowly. They have what we call low myosin ATPase activity. That's the enzyme your myosin heads are using to hydrolyze ATP. They have very low myosin ATPase activity. They're going to burn through ATP slowly, so they're going to move slower. While fast oxidative glycolytic fibers have kind of a little higher myosin ATPase activity. They use ATP a little faster, so they'll be able to move faster. And fast glycolytic fibers have the highest myosin ATPase activity, so they're going to burn through ATP very quickly, and they'll be able to move faster. But there's a consequence. Turns out the faster you burn through ATP, well, the faster you'll get tired and hit a fatigue. So it turns out those slow oxidative fibers, because they're moving or burning through ATP so slowly, it's almost like they're going to have a lot of ATP for a long time. So these slow oxidative fibers could have a long, sustained contraction. So where do you tend to find these cells? Where do you tend to find the slow oxidative fibers? Let me give you a hint. Think of muscles that don't usually move that fast. It's going to be in your back. It's your back muscles again. Your back muscles don't really move that quickly, not like your fingers or your eyelid muscles. They move very rapidly. Your muscle cells in your back don't move that fast. But your back muscles could hold a contraction for a long time. Remember, you're sitting up or standing up because of your muscles in your back. And you could sit up or stand up pretty much all day. Why? Because you have lots of slow oxidative fibers in the muscles of your back. They could sustain a contraction. Your fast oxidative glycolytic fibers, remember, they're a little faster or they have a little bit more myosin ATPase activity, so they're going to burn through the ATP a little bit faster. Think about the muscles in your upper limbs. Some of them have some fast oxidative glycolytic fibers, so they can move a bit faster. But again, because they move a bit faster, they're going to burn through energy a little bit faster and fatigue faster. That's why you can't lift and drop your arms up and down all day, every day very quickly, because they'll get tired after a while. And then there's your fast glycolytic fibers. They're the fastest because they have the highest myosin ATPase activity, so they're going to burn through the ATP rapidly. So these cells are going to get tired the fastest. Where do you find these fast glycolytic fibers? You find them in places like your fingers. Your fingers can move extremely quickly because they have these fast glycolytic fibers. They're burning through ATP quite quickly. That's why you could take notes kind of fast. But if you were to try to write really fast with your fingers, after a while, you'll probably get a hand cramp. Why? Because you've run out of your energy. You've hit that muscle fatigue and cramped up. That's why you can't really write that fast for that long, because you're going to burn through the ATP, because these are fast glycolytic fiber cells. So now you know, not only do you have different types of muscle tissues where the cells look different, within a single muscle tissue, the cells could also look different. And then to finish off this chapter, we just kind of talk about some changes we'll see in skeletal muscle and how you could change it. And then finally compare it to the other two types of tissue, cardiac and smooth. So next thing I mentioned is, how can we change skeletal muscle tissue? Well, there's two major ways to do it. We're talking about training. We're talking about working out. So there are two major ways to work out, at least according to anatomy and skeletal muscles. There's something called endurance training and something called strength training. To help you kind of wrap your mind around it, think of endurance training as aerobics and think of strength training as lifting weights. Okay. So what's some changes we're going to see in endurance training? Think marathon runners, people that run and build up endurance are doing endurance training. This is when you do frequent contractions and you're not focusing on weights. Okay. This is basically running. When you're running, you're doing frequent contractions in the muscles of your legs, but you're not necessarily trying to lift something heavy. You're running. You're focusing on frequency, not the weight of the load. That's endurance training. And when you focus on frequency of contractions, when you do endurance training, you're going to see some changes. Turns out your muscle cells are going to become more efficient at breaking down sources of energy and